thing I would like to say is that this work is in fact a project that started in 2019 and that involved quite a few people, including Marta Belkova, Daniil Kozemachenko, Andrzej Meyer, Krishna Manoka, and Sajad Nazari. So it's really a group work. And the goal of the project was to try and understand what it means to reason with probabilistic information in a paraconsistent framework. So I'm going to first give some preliminaries about Bell-not-done logic. So it's a simple paraconstant logic. That's the one we used. And then I will also introduce paraconstant probabilities. And then I will discuss briefly two-layered logics. So this is kind of going to be the mathematical setup of the conversation. And within that framework, we studied what it means to reason with probabilities and also with imprecise probabilities. So we didn't just look at probabilities themselves, but also how to work with lower and upper probabilities and different notions of probabilities. I will discuss the main results of the project, but here I'm going to try to stay high level, so non-technical. And then I will focus more on the case of belief functions, which is the notion we work the most on. And so in a nutshell, belief functions are a way to talk about lower bound on probabilities. All right. So please don't hesitate to interrupt if there are questions, and let's move on. So first of all, since we want to work in a paraconsistent and I wanted to work in a paraconsistent paracomplete framework, we had to choose the logic. And to start, we chose the simplest one. So we went for Bell-not-done logic, that is basically classical propositional logic without the law of excluded middle and P and not P equal bottom. So it's very close to classical propositional logic. And now the thing is, how do we reason with it? When you reason with classical propositional logic, you ask yourself, you take a formula, P, and you ask yourself, is it true or false in the world? So you have two truth values. If you reason within Bell-not-done logic, the question you ask about the formula is, what information do I have about its truth and falsity? And so you end up having four situations, so four possible truth values. You can have no information, which is the truth value called neither. You can only have information that tells you that the formula is true, only have information that tells you that the formula is false, or you can have contradictory information about it. And so it means that here you get two dimensions. You get how much information do I have that tells me the formula is false or that tells me the formula is true, but also the amount of information, having no information and having too much information. And so one way to look at it is to look at it from the point of view of having two coordinates. So the information supporting the truth of the formula, which would be this one, and the information supporting the falsity of the formula. So if I have 1, 0 has the truth value, I'm saying I have information saying the formula is true and no information saying it's false. 1, 1 is telling me I have both information saying the formula is true and information telling me the formula is false. And what happens there? We have conjunction, disjunction, negation. Conjunction and disjunction behave classically, and the negation is an involutive De Morgan negation. So in terms of semantics, one option is to work over the following models. So you take a set of states, W, and there you put two classical valuations, V plus and V minus. And the first valuation, V plus, is telling you for the variable P, which are the states where there is information saying the formula is true. And V minus is telling you which are the states where there is information saying the formula is false. And from there, you get two satisfaction relations, the positive and the negative one, that behave in the standard way, except for the negation. So if I want to look at a state W to check whether I have information saying that the formula not phi is true, well, I'm checking whether or not I have information saying that phi is false. And so if you look at what happens for conjunction and disjunction, since they behave classically, you get what is expected. So when is it true that at W, I have information that phi and phi prime is true? When I have both the information that phi is true and the information that phi prime is true. And when is it the case that I have the information that phi and phi prime is false? When I have either the information that phi is false or the information that phi prime is false. So basically, you reason classically about the information you have concerning the formula. And so from there, we define the positive and negative interpretation of phi. So the positive interpretation is the set of states that positively satisfy phi. So the set of states where I have information saying that phi is true. And phi minus is the set of states where I have information saying that phi is false. Right, so that was the models I'm going to use to interpret Bell-Nabdon formulas. Now, how can I work with probabilities in this framework? And so here, one way to do it that is very close to what we do with classical probabilities and classical logic is to take this model and add a mass function on W. So a mass function is on W is a function from W to 0, 1, such that the sum of the masses of all the points is equal to 1. So I'm giving a probability distribution on W. And then when I want to define the probability of phi, well, the thing is that now I have kind of two things to talk about phi. I have one thing that talks about the truth, so the information I have supporting phi, and the other negative interpretation that talks about the information I have supporting not phi, so supporting the fact that phi is false. And so what I will have is that my probability will contain two numbers. The first one will be the measure of the positive interpretation of phi. So basically, it's going to represent to which degree my information supports the truth of phi. And the second number is going to be the measure of the negative interpretation of phi. And those two values are independent. So how does this notion of probability behaves? So the first thing to notice is that since we have a nice connection between phi and not phi, in fact, we have that the positive interpretation of not phi is equal to the negative interpretation of phi. That is, the set of states where I have information telling me that not phi is true is exactly the set of states where I have information telling me that phi is false. So P minus of phi is equal to P plus of not phi. So I can just focus on P plus and work only with that and study only this part. And I get for free P minus. So I'm just going to give the axioms for P plus. And so what are the properties of P plus? It's between 0 and 1. It's monotone with respect to the Bell-Nabdon entailment. Oh, there's a typo here. So if phi entails psi, then probability of phi is smaller than probability of psi. And then it satisfies the import-export axiom. And what does this axiom say? This axiom is a weaker version of the additivity axiom you have for probabilities. And sorry, I noticed there is a typo. The macro word is wrong here. It should be psi here, here, and here. So it's telling me that the probability of phi m psi plus the probability of phi or psi is equal to the probability of phi plus the probability of psi. So this is something you have with classical probabilities. The thing is that it's weaker than the additivity axiom of classical probabilities. And then in terms of properties, one thing that you lose is that the probability of not phi is now different from 1 minus the probability of phi. So one important point here is that classical probabilities satisfies the axioms of plus minus probabilities. So you can sometimes have that probability of not phi equal 1 minus probability of phi. But you cannot prove it. It's not derivable. So most of the time it will not be true. And this is something we want because the measure of not phi, the interpretation of not phi is independent of the interpretation of phi in Bell-Natan logic. And one other thing you have, since you reason with a pi-consistent logic, you will have that the probability of phi and not phi. So the amount of information you have supporting the truth of phi and not phi may be strictly bigger than 0. Again, because here I want to talk about the information available and I can have contradictory information. Okay, so in terms of...
Sorry, can I ask just a quick clarification on your arithmetization? So you call normalization the fact that the P plus is between 0 and 1, but I can't see immediately that the probability of a BD contradiction is 0 and the probability of a BD tautology is 1. Is that true?
It's not. It's not. It's just what I say here. Like, it's not the case because if you look at
which is why you don't get the duality downstairs, I understand. But then I have okay, that's perfectly fine. That's what I expected. But then I think it's a bit weird to call that normalization because the sort of the measure theoretic view of normalization is precisely that the empty set gets probability 0 and that so it's just a terminological.
Okay. I accept this.
So that's the range. That's the range of the function rather than the normalization.
Yeah. What will happen, in fact, with what we do, if you look at Bell-Natan logic with bottom and top, so if you expand the language with bottom and top, you will get that the measure of bottom is 0, the way we define it, because there is no state that satisfies the formula bottom, and the measure of top is 1. So you will go back to that. But yes, you need to add those constants to get to this notion of normalization where you say, well, probability of bottom is 0. And
thank you.
Okay. All right. So in terms of interpretation, what happens is when I work with plus-minus probabilities, I'm thinking about Bell-Natan logic and the interpretation of formulas in Bell-Natan logic in this way. So the way I discussed before. So when I think about the true value of a formula, I look at it with 2 coordinates. The first one that tells you how much information I have saying the formula is true, and the second one telling me how much information I have telling me that the formula is false. And if you work with Bell-Natan logic, you just have those 4 points, the 4 truth values. And now with these plus-minus probabilities, basically, depending on the mass function on the model and the formula, you can get any couple of values in this square. And if you work with classical probabilities, the values will always be on this vertical line where the sum is 1. If I take the first coordinate and plus the second coordinate, the sum is going to be 1. But in fact, you can still do the classical probabilities, but you will move to a richer framework where you can also move along the horizontal line, which is talking about the amount of information you have. And so if you are in this triangle, the sum of your plus probability and minus probability is going to be smaller than 1, which means you have some uncertainty and some part of the math you don't know how to assign about on phi and not phi. And if you go on the right side, you start to move towards situations where you have contradictory information. And it means that you move away from this question where you say, oh, when I know nothing about phi, which probability should I take? Well, in the Bayesian framework, you say, well, you start with 0.5, 0.5. Well, here, for us, there's no question. You start here. I know nothing. So you kind of get a richer environment that still includes the classical probabilities. All right. So that was the first way to look about probabilities in the pi-constant framework. And there is an equivalent manner to look at them. which is 4-valued probabilities. So there, what you do is instead of having this plus minus probability, so those two coordinates, to talk about the probabilistic information you have about phi, you give 4 numbers. And so this boils down to looking at the model and creating a partition. So I'm putting in one set all the states where I have only information telling me that phi is true. So we call them the exactly true phi states. The set of states that say that phi is exactly false, so where the information about phi is only saying that phi is not the case. The set of states where I have conflicting information about phi, and the set of states where I have no information about phi. And so then we basically have kind of 4 measures. One for the belief, which would be the measure of the set of states that say exactly true phi. The disbelief in phi, which will be the measure of the set of states that say exactly false phi. The conflict, which will be the measure of the set of states that have contradictory information about phi. And the uncertainty, that will be the measure of the set of states that contain no information about phi. And since I have a partition of the model, those 4 values will sum to 1. And in terms of axiomatization, so we have 4 values sum to 1. Then we have, some axioms that basically describe how the negation encode the behavior of the Bell-Napton negation. So, well, the set of states that say exactly true not phi are exactly the set of states that say exactly false phi, and so on and so forth. And then those 2 axioms are exactly the same axioms as the one we have for the plus-minus probabilities. The first one is monotonicity, says if phi entails psi, then I have the p plus of phi, because p plus of phi is the measure of the sets of states where there is information saying that phi is the case, which is exactly the set of states that say phi is exactly true and the set of states that provide contradictory information about phi. And then this is again just a translation of the import-export axiom. So those 2 notions are equivalent, but they rely on different kind of reading of probabilities. So that was for the logic we are using, Bell-Napton logic, and the kind of probabilities we talk about on this logic. Now, if we want to define logics to reason about probabilities, so there are usually 2 options. You can work with a logic that you enrich with linear inequalities, and another option is to work with 2-layered logics, and that's what we are doing here. So how do you build a 2-layer logic? So you provide an inner logic, Li, that is used to describe the events. A set of modalities that is used to encode the probabilities, and an outer logic that is used to reason about the probabilities. So if I think about the 4-valued probabilities, for instance, my inner logic is going to be Bell-Napton logic, because I choose to reason about in a paraconstant framework. That's what I want to, the kind of events I want to talk about. And then the modalities, I will need one modality for each measure. So one for the belief, one for the disbelief, one for the conflict, and one for the uncertainty. And then I need to choose an outer logic that allows me to write the axioms I need to write about my probabilities. And here we choose Lukasiewicz logic with delta. And so I will not go into technical details in this talk, but for people who don't know Lukasiewicz logic, it allows you to reason on the 0-1 interval. And among other things, you can express the truncated sum and the truncated minus, which means that basically you can write the axioms of probabilities in that logic. So when I want to axiomatize this logic, I need to have an axiomatization of the inner logic. So here's going to be Manhattan logic. An axiomatization of the outer logic, which is going to be here Lukasiewicz with delta. And then I need to provide modal rules and axioms for the modalities. All right. So that is kind of the general mathematical background for the project. And so the main results, so the main things we did. So the goal, to remind you, was to understand what it means to reason probabilistically in a paraconsistent framework. And so the first thing we did was to try and define a modular framework to talk about that, because we wanted to look at different notions of probabilities, because, well, we also wanted to look at different logics. We start with Bell-Nabdon logic because it's a very simple logic, very close to classical propositional logic. But one open question we still have is, well, if we want to add implication, what can we do? What should we do? So we really wanted something modular. And that's one of the reasons we went towards two-layered logics, because they are extremely modular. You pick the inner logic for the events, the outer logic for that works to talk about the notion of probabilities you're considering. And then we wanted to talk about, to look at both quantitative probabilities and qualitative probabilities. And there we noticed that we basically need to understand what the logic, kind of the two-coordinate versions of two-dimensional versions of Lukasiewicz logic that is used to talk about probabilities, and Gödel logic that is one that is used to talk about qualitative probabilities. So we first did some work there in the Tableau paper, and then we moved towards actually developing two-layered logics to reason about probabilities. We worked quite a lot with the plus-minus probabilities and four-valued probabilities. We introduced two-layered logics for them, show that there is faithful embedding between those logics, which you want because the two notions of probabilities are equivalent, and show that the satisfiability of these logics is NP complete. And then, as I said, we want to look at probabilistic reasoning in the wide sense of the word. So we also wanted to look at imprecise probabilities. So there are many, so imprecise probabilities are a way to generalize the notion of probabilities and talk about probabilities when you cannot give the specific probability of each event. So one way to do that is to look at basically lower bound and upper bound on your probabilities. One notion of imprecise probabilities is belief functions that I will discuss in more details in the next sections. And we also did some work on two-layered logics for qualitative probabilities. So now I'm going to focus on belief functions. First, why did we pick belief functions? Because if you look at different notions of imprecise probabilities, they are the ones that are kind of the closest to probabilities. And so it was kind of, if you go step by step, the most natural first step. But then we want to look at other notions such as possibility functions and lower and upper probabilities. Okay, so belief functions are used usually in the framework of theory of evidence, also called Dempster-Shafer theory. So I'm going to first introduce this and then show how you can work with this theory over Bell-Nabdon logic. And I'm going to discuss then some results about belief functions over Bell-Nabdon logic. All right, so belief functions, what are they? There are two ways to look at them. So the first way is to say it's a good notion of lower probabilities. So when I give you a lower probability, what I'm saying is, oh, the probability of A is at least 0.2. The probability of B is at least 0.3, and so on and so forth. So I'm giving you a lower bound on the probability of each event. And if I reason classically, you can easily deduce an upper bound because, well, the upper bound on the probability of A is 1 minus the lower bound on the probability of not A. So usually in the classical framework, I give you a lower bound, you can compute the upper bound. And the thing is, if you work with lower and upper probabilities in full generality, the complexity of the computation is huge. I mean, it doesn't have nice mathematical properties. But if you work with belief functions, you basically more or less do the same computations than what you're doing with probabilities. It's you pay the price of an exponential in terms of computation, but you're still basically doing the same kind of reasoning and computations. And so the axioms that they satisfy, so a belief function over a poor set algebra is a monotone function, such that the belief on the empty set is 0, the belief of the total set is 1. So why do you have that? Is that what is the lower bound on the probability of the empty set? 0. And what is the lower bound on the probability of the total set? Well, I know that my random variable has to take its value in S, so I already know that the measure of this is 1, even if I have no information about the rest. And then there is an infinite set of very ugly axioms that weaken the notion of additivity. And that basically what I care about them is that they allow me to say, well, a belief function, I can also define it this way, and it's equivalent to having this set of axioms. And so the second way to look at it is through the way they do it in the theory of evidence. So there I start with a mass function on a poor set algebra. And so a mass function is a function such that the mass of all the points is 1, and each point has a mass between 0 and 1. And given a mass function, I can define a belief function as follows. The belief of a set is the sum of the masses of all the subsets of A. And in fact, I mean, being a function that satisfies those ugly axioms is equivalent to having a mass function so that I can define the belief in that way. And so I will just work with this from now on. And so the first comment is that if the mass function I'm using is non-zero only on the singletons, the belief function is a probability measure, a classical probability measure. So belief functions generalize the notion of probabilities. And so that's the first thing. And now how do I reason with this? So we're going to look at an example. So the theory of evidence, the idea is that when I get some pieces of evidence of statements, I should be able to encode it via a mass function. And from this mass function, I will deduce a lower bound on the probabilities of the event. And this lower bound is going to be a belief function. So if I consider the following scenario, I have a patient that has a disease A, B, or C. So it means that the set of events is the disease can be A, can be B, or can be C. Here, I assume that the patient has one and only one disease. So it cannot have B and C at the same time. And it has one of them. Okay, so I list all the possible options. And so the doctor says the patient has disease C with certainty 0.2 and disease A or B with certainty 0.5. So how do I build the mass function from this statement? I go on the poor set algebra. So it has disease C with certainty at 0.2. So it means that the probability that it has disease C is at least 0.2. So I put mass 0.2 on C. And it has disease A or B with certainty 0.5. So probability of A or B is at least 0.5. But the thing is that here I don't know how to split this probability between A and B. So that's why the mass is going to be here. If I had a probability measure, I would know how to split this mass between A and B, and would be, for instance, well, probability of A is 0.2 and probability of B is 0.3, and therefore probability of A or B is 0.5. But here it allows me to encode the fact that I don't know how to split. Maybe I cannot measure, maybe I don't have tests to check between A or B. And then the last point is that, well, if you look at those two values, they sum to 0.7, but the mass has to sum to 1. And so what remains of the mass we put on the total set, so on S. Why? Because when I know nothing, the only thing I know is that the disease has to be A, B, or C, because that's how I formalize my problem. And now from this mass function, I can compute the following belief function. And how do I compute the belief function? If I want the belief of A or B, I look at all the subsets, so A, B, A, and B, and I sum the masses. And this gives me the lower bound on the probability measure of each set. All right. Okay, so that is the first step. So we are talking about encoding pieces of evidence. And so the next natural step is to ask the question, how do I combine different pieces of evidence? So here I'm going to give an example where I have contradictory information because, well, if I move toward the paraconsistent framework is to be able to say more things when there is contradictory information. If the information is classical, there's no contradiction, sticking to the classical framework will work very well. So let's take an example where now I have two doctors. The first one says this is A with certainty 0.9 and this is B with certainty 0.1. And the second one says this is C with certainty 0.9 and B with certainty 0.1. So how do I encode each statement? Well, the first one, I put mass 0.9 on A, and the second one, mass 0.1 on B. And for the second doctor, I put mass 0.9 on C and 0.1 on B. So here you can notice that in fact the mass function encodes a probability measure because the mass is non-zero only on singletons. So now how do you combine these things? So there are many options. The first option is to look at non-normalized Dempster-Shafer rule. So there what I do, how do I compute the mass on a point after aggregation? I look at all the couple of sets, A1 and A2, such that the intersection is A. And then I multiply the masses assigned to each set. And I sum all of those and I put that on A. So it's kind of the standard way to combine independent information. So here one hypothesis is that the two pieces of information are independent. And so what you get when you do this is you get most of the mass on the empty set because basically the two doctors disagree. Okay. One other option is to use the normalized version of Dempster-Shafer combination rule. And what does this do? It ignores contradiction. So basically it takes the mass that was on the empty set, we throw it away, and then we normalize so that all the masses sums to 1. This rule was given with very strong axioms. In fact, the framework in which it was proposed was that the experts are fully reliable, which means that when the first doctor says C is not the case, okay, because this implies that C cannot be the case. It means that C cannot be the case. And when the second doctor says that A cannot be the case, it means that A truly cannot be the case. And therefore, here, the only rational conclusion is that they both agree on the fact that B is possible, even though unlikely, so B is the case. And within those assumptions, you get an intuitive conclusion. Now, if you are not within that framework, which, well, for instance, I will not make those assumptions because I assume I have contradictory information. Therefore, I assume that my experts make mistakes. Then you reach conclusions that you do not want to reach. Basically, here, if you assume they can make mistakes, you want to say, oh, well, it's most likely A or C. B is possible, but unlikely. And then there are other options that, for instance, says, well, the mask that was initially sent on the empty set, so contradiction. Well, contradiction boils down to having no information, so we move the mask to top. And there are many variations. And in fact, what I can say is that in the classical framework, they really developed a theory that works very well when they are able to assign confidence on the reliability of the experts. So when they know how reliable the experts are, there are very good combination rules that give very good conclusions. But when you cannot say anything about the reliability of the experts, it's quite difficult because basically, how do you decide where to put the mass and what to conclude? And I really think this is where this framework that we introduced can be useful, because even though, even if I know nothing about how reliable the experts are, if I move toward a paraconsistent framework, I will be able to say on which topic they disagree, on which topic they agree, how much they disagree. And so that's what we're going to discuss in the follow-up.
Sorry, can I ask you a quick
Yeah,
question on the,
sure.
The independence assumption seems to be very strong here as well. I mean, I understand you sort of assume they don't talk to each other, right? But presumably they're looking at the same patients. It's a bit,
Yeah, I mean, well, it's the same patient, but no, I agree that the independence assumption is very strong. But I mean, these computations you do with probabilities when you have independent pieces of information. So we started from the beginning. And so if you look at the first works on Dempster-Schiffer theory and the simplest rules you can have there will be with assuming that you have independent sources and trying to aggregate that. I agree that in many situations, they are not independent, but we haven't looked at that yet.
Sure.
So, all right. So now, what do you get? How do you define Dempster-Schiffer theory over Bell-Lambda logic, and what do you get? How does this behave? So to define, one way to do it is very natural. Is you start with the model, the Bell-Lambda model. And initially, when I was working with probabilities, so I had my set of states, my two classical valuations, and a mass function on W. So I had a probability distribution on W. Well, now, since I want to work with a belief function, I put a mass function on the poor set of W. And from this mass function, I will be able to get a belief function on the poor set of W. Now what I want is a belief on the formulas, all right? So basically, I'm trying to define a belief function on the Lindenbaum algebra for Bell-Lambda logic. And well, how do you do that? The standard way. This is very natural. You take the belief in the positive interpretation of phi, and we can show very easily that this is going to be a belief function on the Lindenbaum algebra. I have to make a small comment here, is that we worked constantly with a finite set of propositional variables, which means that the Lindenbaum algebra is finite, and we didn't look at the mathematics in infinite situations. So you get the positive belief on the Lindenbaum algebra and the negative belief that encodes how much information you have saying that phi is false. And if you want to talk about aggregation, how to combine the pieces of evidence, well, the first thing that you can notice is if you look at Dempster-Schiffer combination rule, so it was so this thing with normalization, which is like the standard thing. You test every time you proposal rule, you compare it to Dempster-Schaeffer combination rule. There's no talking about normalization, because if you take like the initial but not done logic, there's no bottom. So you don't have contradictions, so you don't have to ask yourself the question, oh, what do you do with the math that goes on bottom? If you want to extend Bernardon logic with the constant bottom and top, then you, again, need to decide whether or not you want to normalize, therefore have belief of bottom that is 0 and handle it. All right. But if you just stick to this, you don't have to ask yourself this question. And so which kind of behaviors do you get? And here I'm just going to stick to my example and look at what happens when I encode it within Bernardon logic. So I still have my patient that has one and only one disease, and my 2 doctors that give those statements. So the first thing is that now I need to be careful. When the first doctor says this is A with certainty 0.9, on which set of states do I put the mass 0.9? I could put the mass 0.9 to the set of states that satisfy the formula A, so where I have information that A is true. But if I want to formalize the initial statement where my doctor was kind of reasoning classically and says, if it's A, it's not B and not C, I have to put the mass on the set of states where A is the case and not B is the case and not C is the case, okay? And then for the doctor saying B with certainty 0.1, I put the mass on the interpretation of the formula, not A and B and not C. And then I do the same thing for the second doctor. And when I combine the information, now most of the mass is going to be on this set. So this is the set of states where I have contradictory information about A, contradictory information about C, and the information that B is false. Which, I mean, is a good description of the information I have. I have my 2 experts and they disagree about A and C and more or less agree on the fact that probably it's not B. But I will still have some mass on states where B is the case. And so if I look at the belief function, I get that the doctors agree with the fact that the patient most likely does not have B, because the belief in not B is very high, 0.99. B is still possible because the belief in B is 0.19. The evidence strongly supports A or C, but it's also highly contradictory about A and about C. So since my mass functions are symmetric, the belief in A and not A is equal to the belief in C and not C. So since I didn't have the space, I didn't put it there. And I have contradictory information about B, but not that much. And so what I gain by moving to the Bernardon framework is that now I'm able to quantify not only the information I have about A, B, and C, but also how much contradiction I have about each variable. And again, I want to add the caveat that in the classical framework, when they are able to grade how reliable is a source, they really can solve that problem just because, well, you know, if it's unreliable, you modify the mass function that's associated to it and you get very good combination rules. So, yeah. All right, so what did we show? We designed an expansion of Bernardon logic to talk about belief and plausibility functions. So the belief function gives me the lower bound on the probabilities, and the plausibility function gives me the upper bound. So in the classical framework, the upper bound on the probability of A is 1 minus the lower bound on the probability of not A. Here, things get a bit more complex because you don't have a classical negation, so that's why I don't go into it in the presentations. Then we proposed both a logic with linear inequalities and logic with a 2-layered modal logic to reason about belief and plausibility. And we prove the completeness of both calculi and their equivalence. And so this was like kind of the long technical logic paper. And we also wrote a paper that was we sent to the conference on imprecise probabilities. So it's not a logic paper, where we try to connect with what is done in the classical case. So basically there we discuss how to encode different kinds of pieces of evidence. And we show how Dempster-Shafer rule behaves, in which situation we are very happy with his behavior when it gives unintuitive results. We also propose a variation of Dempster-Shafer combination rule. But the point we make there is that it's not that it is better, it's that since we are in a different framework and a richer framework, we can use the bilattice of the truth values to introduce new rules and talk about different situations. And finally, point that for me is very important is that we show, so what do you do when you work with belief functions in the classical settings? I mean, usually the belief function gives you a lower bound on the probability of an event, and you deduce the upper bound. And so it gives you a non-empty set of classical probability measures that are coherent with your evidence. So basically, I assume if someone works with belief functions, what they want their conclusion to be is that, okay, this is the set of classical probability measures that are coherent with my evidence. And what we show is that if you start with your problem, with your different experts, you encode what they tell you in the framework of Bernardon logic, then you still have reasonable ways to extract a classical belief function, and therefore to extract a non-empty set of classical probability measures that are coherent with the pieces of evidence. And I have the slides, but I don't have the time to go into the details of how we do this. But I think this is very important because it's a way to reconnect what people are actually doing in applications. And thank you for your attention.